Now that we've learned about molecular orbitals, we can relate this to bond strength. So here is our molecular orbital diagram. Again, that we talked about in the previous video, where you take psi of HA and psi of HB, you bring them together, you form a Phi bonding and Phi antibonding, right? And we see that the bonding orbital, the new bonding molecular orbital that's created, is lower in energy. Now, how much lower in energy relative to the atomic orbitals we can actually measure. And that measurement for hydrogen, it happens to be 104 kilocalories per mole of hydrogen that's being produced. So, to review some definitions that we learned in general chemistry. When two hydrogen atoms come together to produce hydrogen, 104 kilocalories per mole of energy is released. This is called an exothermic reaction. And so when we talk about exothermic reactions, we talk about enthalpy. And we say that the delta H, or the enthalpy, is minus 104 kilocalories per mole. Why is it minus? Because energy is released. So remember, the system is giving up energy to its surroundings, and therefore the sign is negative. That's when we're talking about two hydrogen atoms forming hydrogen molecule. Now, we could also think about the reverse process. When a hydrogen molecule makes two hydrogen atoms. Well, in order to do that, we have to break that bond. And to break hydrogen into two hydrogen atoms, it requires 104 kilocalories per mole of energy. This is called the bond dissociation energy. And oftentimes you'll see it abbreviated the BDE, the bond dissociation energy, BDE. So it's important to understand, when you see that abbreviation BDE, that's referring to the bond dissociation energy. It is always positive. It's the energy required to break that bond. And therefore, that's why it is a positive value. So bond dissociation energy always refers to a homolytic cleavage. Now, what does that mean? That means that there's two electrons in that bond, right? So we can have one of two possible breaks, bond breaks. The first one is called a homolytic bond break. So if I have a hydrogen molecule and in that bond, one electron from that bond goes to one hydrogen and the other electron goes to the other hydrogen, that is called a homolytic breakage or a homolytic cleavage. Each atom is getting one electron. Notice the arrows that I use. I'm using the fishhook arrows because I'm denoting the movement of one electron in one direction and one electron in the opposite direction. And the result is I get two hydrogen atoms. Now, the other possibility is what we call a heterolytic cleavage. And we're going to see both homolytic cleavage and heterolytic cleavage throughout the semester. So it's important to understand the difference between the two. In a heterolytic cleavage, if I have hydrogen and both electrons go to one of the atoms, so let's say the electrons, now notice I'm using the double barbed arrow, and so both electrons are going to the hydrogen on the right. The result is that the hydrogen on the left now has no electrons, and so it's simply a proton, while the hydrogen on the right has both electrons and it has a negative charge. It is a hydride. So the result of a heterolytic cleavage gives me a proton and a hydride. When I compare the two, and we said that bond dissociation refers to homolytic cleavage and not heterolytic cleavage. The reason for this is because in a heterolytic cleavage, you get two charged species, whereas in the homolytic cleavage, you get two neutral radical species. Okay, so it's important to understand that bond dissociation is always the homolytic cleavage between two atoms. Now, there is a table in your textbook, table 1.10, and you should take a look at that. One of the things that you need to notice are some of the trends, and I'm going to highlight some of these trends that we're going to see repeatedly. The first trend is the bond energy between carbon and a halogen. So if we compare all of the carbon-halogen bonds, we see that the carbon-fluorine bond is the strongest. It's stronger than a carbon-chlorine bond, and the carbon-chlorine bond is stronger than a carbon-bromine bond, and the carbon-bromine bond is stronger than the carbon-iodine bond. So again, you can refer to table 1.10 for the values. Now, I'm never going to ask you to memorize the values, the explicit values, but I want you to certainly know the trends and to know why these trends exist. Now remember, I said that molecular overlap it becomes weaker when the energy of the two atoms and the size of the two atoms changes, right? So as I go from fluorine to chlorine to bromine to iodine, I'm moving down the periodic table. The principal quantum number is getting larger, right? And the size of the atom's getting bigger. And the result is when I'm looking at a bond between carbon and one of those halogens, there's weaker overlap between the orbitals with different principal quantum numbers. So fluorine has the same principal quantum number as carbon, and therefore it has very good overlap, very strong overlap, and the bond is stronger, which means the bond dissociation energy is larger, right? It requires more energy to break that bond. Another trend that I want you to notice deals with the different types of carbon-carbon bonds. So a carbon-carbon single bond is less stable, it has a lower bond dissociation energy than a carbon-carbon double bond. And a carbon-carbon double bond has lower bond dissociation energy than a carbon-carbon triple bond. Why is this? Well, very simply, more bonds requires more energy to break those bonds. And therefore, the carbon-carbon single bond is, in a sense, a weaker bond, even though it's a very strong bond. And we're going to see it's actually pretty hard to break that bond chemically. So this gives you a little insight into bond energies, what those bond energies mean in terms of the molecular orbital diagram and kind of that picture of how molecular orbitals are produced and what that entails in terms of energy.